All right, so what we're looking at now is that we're going to be moving on into the mathematics of money, and we're going to be looking at interest rates and savings accounts and loans. So this is a very important chapter based on whenever you take out student loans, when you want to take out a loan to buy a car or buy a house, when you start a retirement fund or a trust fund for somebody. This is stuff that you're going to have to make sure you know before you start to do this. So first thing with saving money is whenever you go to a bank, banks have savings account that you can open. A lot of them, you open up a checking account and a savings account. And what you want to do is you want to make sure that each of these banks fit what you're looking for. Some of them will charge if you have, under a certain amount of money in it. Some of them will have a lower interest rate on their savings account. Others will have larger. It all depends on what you are looking for in a bank and what you need in a bank to help you succeed and save money for the future. And these banks also are the ones that will, if you ever want to take out loans or anything outside of government loans, if you want to take out private loans, banks are usually the big one to be able to do that. Now, the first thing that we're looking at is with savings, with simple saving or simple interest rate. What simple interest rate is that you're focused on just the original amount that you put in. Now, this formula here, F is your final, P is your principal or your original amount. All right, so P is the original amount that you put in. R is your interest rate, so the rate that you're gaining money, and this is in decimal form. So 5% you would say is 0.05. All right, that would be 5%. You would put that in the decimal form. And T is the number of years. Typically, it's the number of years that you have. Now, in simple, usually with these simple interests, they usually are on a year-by-year gaining interest each year. It's only once a year. And so let's say we have $500 that we've invested in a bank, and it's 5% and it's simple interest. After the first year, they're gonna add 5% of $500 into our account. So we would take, basically you would take 500, multiply it by 0.05, and that gets you about that 25%. So they would add 25, so you would end up having 225. The next year, they would give you 25 more dollars. So it would be 250. And then it would be 275, and so on and so forth. And as you see, it grows at a constant rate. This is a linear function that grows at a constant rate. So every year you're going to be getting $25 in this case. Okay, so it's based on the original amount that you put in. Now, the other one that we have is compound interest. Now, compound interest is different. It's more of an exponential growth. All right, so it grows faster. It's usually what you'll see with many savings accounts, and it builds on what you have at the moment. And again, this formula, F is the final, P is your original amount, R is the rate, again in a decimal form, T is the number of years, N is the new variable here, and N is the number of times a year you're compounding it. You're compounding this rate that you have. Okay. So sometimes you'll hear, okay, it's compounded weekly, or it's compounded daily, or it's compounded monthly, or bi-monthly, or tri-monthly. I mean, it depends on whatever the situation is. And what compound interest is doing is that if we do the same thing, that 5% for $500, after the first month, it's going to be the same amount as in simple. It's going to be a 525, the gain of 25. Now, the next one, we're going to take 5%, or a smaller percentage, after the next year, or if it's compounded, if we're doing it annually, it would be 5% of this amount, of this 525, which ends up making you about $551 and about 67 cents, somewhere around there. So as you see, it grows a little bit more. And then the next year you'll take 5% of this amount. And then the next year you'll take 5% of that amount, and so on and so forth as it gets larger and larger and larger. So as you see, you'll get more money doing a compound interest because it's based on how much is in there at the moment and not the original amount. Okay, now, this part right here you saw in the compound interest formula, the R over N. And what this is this helps you find the actual rate each time they're compounding the interest. Now, whenever you watch a commercial and they deal with some sort of interest rate, they use something that we're calling the annual percentage yield, or the APY. And the APY is like, if I say, okay, we've got 5% and it's compounded monthly, okay, the actual amount that we're getting interest for each time that it's compounded would be 0.05, or the decimal of the rate, divided by the number of times a year, which would be 12. So we would be getting about 5/12 of a percent each time that it's compounded in a year. Okay, we'd be getting 5/12 of a percent. And each of these change depending on how much. As you see, if the more times you compound it, the smaller that number gets. But the trade-off with that is that since you're doing it more, you end up, in the long run, you end up getting more money each year the more times you compound it. So now the question is, well, if we compound it non-stop, so it's, continuously compounded, well, does that mean we'll end up getting almost an infinite amount of money? And the answer to that is no. Sadly, you do not. What they have found out is that if you were to continuously compound the money, what happens is that you end up hitting some sort of ceiling. You hit a top of how much you can make. And to find this, the easiest way of doing it would be, let's say we had $1 and we invest it at 100% interest. So after the first year, if it's compounded only once, we get $2. And we want to look at how much we'll have after each year. So if it's compounded annually, so once a year, we'd end up with $2. If we do it 12 times a year, we end up with about $2.61. If we do it weekly, we end up with about $2.69. If it's daily, we were with about $2.71. Minutely and hourly and secondly, we would end up with, or hourly and minutely, we would end up with $2.71, $2.72. And as you see, these numbers are almost identical down to the hundredth of a cent. So they're still the same. And as we get more and more and more and more and more and more and more, what happens is that these numbers become more and more alike, and there is no change. And this leads us to the formula for continuous, which you've probably heard as PERT. Some of you might have heard it as NEKT, N-E-K-T. But we are going to use PERT, which is the principal times E, which is a constant. We'll talk about that in a second. Times to the power of the rate in a decimal. So this is again like 0.05 times the time, which is the number of years. Okay, and this right here is the APY. All right, so that is our continuous formula. Now, the Euler's number, which is this number that we got, this 2.71828, blah, 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 and it continues on into infinity. It's a rational number just like pi or phi, the golden ratio, or to help us find the circumference of a circle. And this is called Euler's number, even though Mr. Euler over here did not discover it. It was actually discovered by John Napier, who worked with a lot of logarithms and natural logs and other in that branch of mathematics. And he was the one that actually discovered this, and he discovered it by taking, if you take the limit, okay, I'm going to get pretty technical with math here, the limit as n approaches infinity of our compound interest formula, 1 over n to the n. If you take that and take it off into infinity, so if n keeps getting bigger and bigger and bigger, what happens is that we approach this number. And that's what he discovered when he was working with these logarithms. And Euler's name is attached to the number is because he was the one that started using this letter E. He was the one that used the letter E and now he's the one that a lot of people think is the one that created the number. But he was the one that just used that coefficient.